students. Today we will start with the fourth module here, part 1, point sources and errors here. Today we will discuss regarding the definition of the point source here, and we try to understand regarding the point source as an antenna here. And next we try to understand regarding the power theorem here. Thereafter, we try to understand the power pattern here, and thereafter the arrays of two isotope point sources we will try to understand today here. The four topics we'll discuss today. So that is point sources, power pattern, power theorem, and arrays of two isotopic point sources here. So in this particular module 4 here, point sources and electric dipoles have been discussed here. So initially we will discuss point sources in the part 1 here. So what is this point source here? Okay, an antenna is considered as a point source here. Okay, so what is exactly the meaning of this is antenna as a point source? So whenever we say that antenna could be of material of different sizes here, so what we are going to consider in this case here is we are just going to consider a dot or a point as an antenna here, which is nothing but here. It is nothing but which is going to generate certain energy here, which will be in terms of point here. Okay, point source it is called as, right? So this same point source, okay, the concept is extended to formation of array of point sources here. Hence, whatever the formation of array of point sources is there, okay, in a linear fashion here, okay, this pattern of any antenna can be regarded as an array of point sources here. Okay, so and what is the meaning of array of point sources here? Nothing but here a point source is nothing but here we will consider it as a source here, okay, or radiator here, okay, or energy radiator here, or antenna here. Okay, so which is just a point source, very small in size here, right? The same antenna which is very small in size, if it is been arranged, okay, in a linear fashion here, or in a formation of an array here, okay, hence that pattern of an antenna, okay, can be regarded as array of point sources here. Now let us discuss the very important concepts regarding the point sources here. You can see in the particular figure here, point source. Okay, whatever the fields or whatever the energy that is been generated by the point source here, usually what you can say that in the near field and the far field we have discussed here in the antenna basic parameters here. In the near field, what is going to happen here is the power flow will be there here, and that power flow from the particular point source will be radial in nature here. But uh, in the far field here, what is going to happen? The same power flow will be little bit of what you can say that depends on the distance here. Okay, so now let us understand this particular figure here. Figure A, you can see in this figure A there is one observation circle here. This is a circle that has been indicated here. Okay, on this particular circle here there is a point called as a Q here, which is the observation point you can consider here on this circumference of the circle here. And there is something called as a midpoint here, okay, center of the circle here, where exactly our point source antenna has been placed here. And whose label we can consider as O here. And what you can consider is R is nothing but here the radius or the length between the center and the observation circle here. Okay, so now what is it now is whatever the energy or the power or the waves that has been generated by the point source here, or you can say valueless emitter here. We can also call it as a valueless emitter here, which is placed at the center of the observation circle here. Okay, so whatever the actual field will be there here, the near the antenna, usually we ignore here whatever the variations that we are having in this particular near field of a particular antenna here, we'll ignore here. And we always what you can say that we consider or describe the particular source here, okay, considering the waves in the far field here. How much energy or how much power that is being produced by a particular point source in the far field, that we will be considering here. Okay, or source will be described in terms of the far field here. Okay, Now, whatever the field measurement is there, okay, around this observation circle here, okay, if at all we have an antenna which is fixed at the center or the center of the circle here, then we will not be having any change in the field measurements here from the point of observation circle here. If the Q is at this point, the field measurement will be same from the point of center of the source here, or the Q is at this point also. Okay, so the field measurement will be same here if at all the antenna is fixed at the center of the observation circle here. Okay, now if at all this antenna, it starts moving with a certain distance called as a D here. Okay, here in the figure B you can see point source antenna here. If at all from the center of the circle here, that is represented as a O here, okay, if it starts moving here with a certain distance D, then what is going to happen here is that there is a change in the phase here. If at all the D, whatever the distance D is there from the center of the observation circle O to this particular point source antenna here, if the D is equal to 0, that is nothing but here our antenna is at the origin of the observation circle here. Okay, so if it is there, then whatever the phase shift will be there, it will be minimum here. As and when the distance D is going to increase here, this distance, if it is going to increase here, then there is a phase shift will be there here, and that becomes very large here. If at all we wanted to describe a particular source in the far field here, there are three patterns which we need to understand from the point of describing the particular source in the far field here. Okay, what one pattern is regarding the field pattern here, that is concerned with the E theta, and the second one is E phi. The third pattern is phase here, that is represented by the delta here. So there are three patterns here which we need to understand if at all we wanted to describe or give a description of a particular point source, that too considering the far field here. So that is two field patterns and one phase pattern is required here. Okay, this is what is just an introduction concerned with the point source and point source related explanation here. Okay, so let us move on to the next topic here. Next, very small topics are there here. Let's power pattern here. So what is this power pattern here? Okay, so let us consider that there is a transmitting antenna here, which is in a free space here, and it is represented by the point source radiator. Point source radiator at the origin of the coordinates here, as you can see in this particular figure here. See this point source at the origin here. Okay, which is being placed at the Z or X and Y axis here. Okay, you can see here theta and phi are in the particular direction it is been pointing out here. Now, what is this SR here? SR is nothing but a radial component. Radial component usually is nothing but a pointing vector here. Pointing vector is nothing but here, what you can say that it is nothing but a power density here. Or you can say in another definition here. What is the definition of this pointing vector here is, we can say that it is a quantity here which is going to what you can say that describe the source magnitude and the direction here, or you can say that a quantity which describes the magnitude and the direction of a flow of energy in electromagnetic waves here. Okay, so it is going to decide magnitude and direction here. Okay, so in that case here, it is watts per meter square. We can also say that it has a power density here. Power density at what particular point here, that is R with theta comma phi here. Now, from a point source here, that there is a pointing vector S here, and as only a radial component, as we can see here, it is having only the radial component as SR here. We are not considering any component theta or phi here. So if at all we are not considering any theta or phi here, so S theta and the S phi is equal to 0 here. We are not considering any of the components in the theta and phi direction. We are considering only in the direction of R here. So hence SR will be having certain value here. So the magnitude of the pointing vector, or we can say that the power density is equal to the radial component. You can say here, whatever the power density is there, it is equal to the whatever the radial component which we have described here. So if at all we consider that isotropic source. Isotropic source means what you can say, which generates uh, energy or the what we can say that power in all the directions uniformly here. Okay, so whatever the SR is there, SR is nothing but here it is independent of theta and phi here. That means it is not. It is one. It is in one particular direction here. It is not distributing uniformly the energy in all the directions here. So whatever the SR is there, a graph of SR, that is pointing vector in the direction of R here at a constant radius, okay, as a function of angle, is a pointing vector called as a power pattern here. Okay, so you can see this particular below figure here. This is SR here. Okay, so SR is independent of theta and phi here. Whatever the graph we are going to draw with the component SR here, okay, as a function of a pointing vector here with a constant radius is called as a power pattern here. Okay, if at all we have a three-dimensional view, it may be considered as a power pattern for an isotropic source in a sphere here. If at all it is a two-dimensional, then it is considered as a circle here. Power pattern is a circle. How exactly the power pattern will look like if at all we consider a sphere or a circle here. Okay, if at all we consider it is a three-dimension, then definitely it will be look like it is around a sphere here. If at all we consider a circle, it will be the two-dimensional here. So if at all we consider the power pattern of anisotropic source here. Anisotropic source means in one particular direction here. Where isotropic is nothing but here generating radiation or energy uniformly in all the directions here. Okay, so where SRM is the maximum value of SR here. So you can see here SRM is nothing but here maximum value of the SR component here, which will be there in one particular direction here. Okay, so suppose the whatever the SR component is there, if it is been expressed in watts per square meter, then it is considered absolute power pattern here. If at all if it is been compared with some other reference direction here, then it is called as a relative power pattern here. Or if at all the pattern is having a maximum power as a unity here, then it is called as a normalized power pattern here. Remember, absolute power pattern, relative power pattern, and normalized power pattern here. So this is what is regarding the power pattern here, power pattern for the antenna here. Okay, that too point source antenna here, and one particular direction here, that is SR component. Okay, now that is regarding the power pattern here. Let us understand regarding the power theorem, which is very important again. Pointing theorem, this is the definition which we have here. Pointing vector is the thing, but again I have told you in just a few minutes before. Pointing vector is the thing, but here, which is going to describe the magnitude or the direction of a flow of energy here. Flow of energy into electromagnetic wave here. It is going to describe here the direction with magnitude here. So pointing vector means we know the direction and the magnitude of the particular energy at all points here, at all points on a sphere of radius r here, on a sphere of radius r from a point source in a lossless medium. Then what is exactly the total power? The total power radiated by the source is nothing but an integral over the surface of the sphere of that particular radial component SR of the average pointing vector. Here, this is how it has been described here. What is exactly the power theorem? Power theorem is nothing but here the total power radiated by the particular source. Okay, particular source is the integral over the particular surface of the sphere, the radial component, okay, SR of the average pointing vector here. Okay, so that has been given by the equation P is equal to double integration of circle. You can say that the double integration S into TS here. What is P here? Power radiated. S is nothing but here. You can also replace with SR here. Equation number 1, you can see SR is nothing but here a radial component here in one particular direction they are going to consider here. Okay, so of average pointing vector watt per meter square here. TS is nothing but here a very small infinitesimal area here, which is we can have r square sin theta d theta d phi here. We can also write it like this also here. Area of a sphere here, you can write small elemental area here. Okay. Now if at all we consider the for an isotropic source here, if at all we can consider isotropic source, means it is generating radiation in all the directions here, where we consider only SR is independent of, in this case SR is independent of theta and phi here. Okay, if at all we consider it is independent, then what you can write here is SR is if it is independent, then we can write it as SR is SR into 4 pi r square here into watts here. So SR is equal to P divided by 4 pi r square here. So equation 3, what exactly the equation 3 is going to indicate here is that it is going to indicate that the magnitude of the pointing vector is going to vary inversely as the square of the distance from the point source radiator here. SR is inversely proportional to P divided by 4 pi r square here. Okay, this is how we can describe regarding the power theorem here. Okay, so power theorem is nothing but here we can say that power radiated, total power, how much it has been radiated by the particular source here, is equal to integration of the radial component. Okay, radial component, considering that the radial component is independent of theta and phi here, that has been given by SR is equal to P divided by 4 pi r square, or P is equal to SR into 4 pi r square here, which could be watts per meter square here. Okay, per meter square here. Okay, this is how we can explain the power theorem, which is going to be asked for 5 marks in the exam.